Today we're talking about complex numbers. Another blast from the past. You've been through this before. So back in the day, when you were first learning about numbers, we had our natural numbers, and those were our counting numbers. We learned how to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you were my son, you skipped number 7 for some reason, and away we went. So those were your natural numbers. We added the number 0, and that was your whole number system. And that was the day that you learned, oh no, there are no more suckers in the bag. You can't have one today, or something of that nature. There are 0 left. So it was a sad day on those days. And then you learned about integers. And those integers are those counting numbers that we were talking about, the 1, 2, 3, 4, 5, 6, 7, and the whole number 0, but also those negative pesky numbers that were the reason why you couldn't go out sledding when it was -3 degrees outside. It's too cold to go outside. So negatives are our negative counting numbers are added when we are talking about integers. Then you learned in about 3rd or 4th grade, maybe before that, we were talking about pizza and how much pizza do we have here. Well, there are 8 slices, and when we have one of those, we're eating 1/8 of a pizza. And when half of the pizza is gone, you talk about fractions basically, and you start learning about money. $5.53. 53 cents is a decimal. So those are your rational numbers. And then about, I don't know, 7th or 8th grade maybe, you learn about this number called pi. And this number called pi is our first irrational number that we're really exposed to, along with things like the square root of 2, or the square root of 5, or negative square root of 7. Okay, we'll learn about, and we've learned about in Algebra 2, another rational number called e, and we'll work with that this year. And those are numbers that don't ever terminate, don't repeat, okay, non-terminating, non-repeating numbers. So they're kind of off to the side. They don't become a part of these rational numbers, and that's our real number system. So up until today, we've been saying there are 2 things that we can't do. What are the 2 laws we can't break? Can't divide by 0. That's still going to remain in effect. Okay? You're breaking the law there. And the other one was square root of a negative. Okay? We can't take a square root of a negative. And you're like, wait a minute, we did that in Algebra 2. We know how to handle that. Well, now we're going to handle that again. So we're going to move out of the real number system, okay? Because most of what we were doing was graphing things, right? We don't typically graph a negative square root. So today we'll talk about the complex number system, because we get to introduce imaginary numbers. So our numbers like 7 and 15 are still here, but now we have our lovely imaginary numbers. If it helps you to sketch it, great. But if you don't need the picture, if it's kind of fixed in your mind, or you have a different way of visualizing complex numbers, by all means. So I is that number that stands for the square root of a -1. And we know that the standard form of a complex number is a plus bi, where a is the real part and b is the imaginary part. All right, so I helps us solve equations like x squared plus 4 equals 0. X squared minus 4 equals 0 is easy. We could factor that into x plus 4, x minus 4, the difference of squares. But when we have x squared plus 4 equals 0, we run into a problem. So we have to remember that I stands for that square root of a -1. So every time we get a square root with a negative in it, we pull that square root of -1 out, call it I, and then deal with what else was inside of that radical. I squared is nothing more than the square root of -1 squared. And we know that if we square a square root, whatever was underneath the radical is our answer. And when we have I cubed, that's nothing more than I squared times another I. So we'll have a -1 times an I to get I cubed. And then finally, I to the 4th is nothing more than negative I times another I. And negative I times another I is negative I squared, but we said that I squared was a negative 1, so negative negative 1 is positive 1. Okay? Everybody remember this? Okay? And then it just keeps cycling through. If it's divisible by 4, it's going to be an I. If it's not divisible by 4, it has a remainder of 2, for example, it will be a negative 1. If it has a remainder of 3, it would be a negative I. Okay, so here we go. We're going to, first of all, remember how to add and subtract. So if we have the complex number 6 minus 3i, and we're adding the complex number 1 plus 2i, what do we do? Looks just like algebra, doesn't it? We're combining our like terms. The 6 minus 3i and the 1 plus 2i, which are like terms? 6 and 1. So what is 6 plus 1? And negative 3i and positive 2i are like terms. So what is negative 3i plus 2i? Negative I. And we're finished. We have our a plus bi form of our complex number. Okay. If we have 5 minus I and we're subtracting 2 minus 4i, what do we have to remember to do? Yeah, don't forget to distribute that negative. So this is 5 minus I minus 2 plus 4i. Now our like terms are our real portions, right? So 5 minus 2 is, and negative I plus 4i is, okay? So nothing too scary there. All right, now we're going to multiply. So now we have a real number 2 taken times a complex number, 14 minus 3i, or 2 complex numbers. This one just doesn't have an imaginary part, it only has a real part. And when we do that, what do we need to remember to do? Just like in algebra, we have to distribute to both. So we take the 2 times 14 and we get, and the 2 times a negative 3i and we get, what's a negative 6i or minus 6i? Most of us are used to just writing minus 6i. Okay. Letter B, we're taking 2 complex numbers and multiplying them by each other. So what do we do? FOIL it out. 2 times 4. Outside's 2 times 3i. Inside's negative I times 4. Last, negative I times a positive 3i. Good. And that's where that little chart is going to come into play. So first we'll combine our imaginary parts. We've got 8, and we have a plus 2i. But what was I squared? Negative 1. So negative 3 times a negative 1 is, and so 8 plus 3 is 11 plus 2i. Okay. All right, what do you have to be careful about with part C? Those are 2, so we don't want to forget to FOIL it out, write them out separately, or remember our shortcut. When we're squaring binomials, we square the first one. So what's 2 squared? Then we multiply these guys together and then double them. So 2 times 5i is 10i doubled is, so 20i. And then we square the last term. What is 5i squared? 25i squared. So 25i squared becomes, I squared is actually -1. So we'll have a -25. -25 and 4 is, so -21 plus 20i. And again, if it helps to just rewrite it as 2 plus 5i times 2 plus 5i and FOIL it out, by all means do that. Okay? All right, letter D. How are we going to simplify letter D? Taking a complex number times a complex number, so we FOIL it out. What's 3 times 3? And then 3 times a positive 2i? Negative 2i times 3? And last times last, negative 2i times 2i. Negative 4i squared. Negative 4i squared is the same thing as plus 4. So negative 6i and positive 6i are going to cancel, and 9 plus 4 becomes 13. Why did we lose our complex part of that our imaginary part of that complex number? What made it go away? Yeah, they were exactly the same but opposite signs, right? That's like the difference of squares, isn't it? That's what makes that middle term go away. And these are what are called complex conjugates. Okay. Just like we learned yesterday, something like 4 plus the square root of 5, if that is a 0 or a root to our equation, it travels in a pair with 4 minus the square root of 5. They go together. Complex conjugates also go together when they're a solution to an equation. Okay, travel in pairs. So, two numbers of the form a plus bi and a minus bi are called those complex conjugates we just mentioned. The nice thing about them is their product is a real number. The imaginary portion is gone. Okay, so when we know that, we can utilize that to help us simplify things. Because whenever you were working with radicals before and fractions, we always wanted to rationalize the denominator. We didn't like to leave a radical in the denominator. Remember that? Okay, so if we had something like 3 over the square root of 2, we had to multiply it by root 2 over root 2, right? That made the square root in the denominator go away, and it moved it to the numerator. So we would have 3 square roots of 2 over 2. If we had something like 4 over 1 minus the square root of 2, what did we have to multiply that by to make the radical go away? 1 plus the square root of 2, because just the square root of 2 would have introduced it to the 1, not to both. So we would multiply that by 1 plus the square root of 2. And when we FOILed out the denominator, we got 1 minus 2, or a -1 when it was all said and done. And we had 4 plus 4 square roots of 2 on the top. So then it simplified and we no longer had a radical in the denominator. Well, it's no different here. This I stands for the square root of a -1. So we don't like to leave that in the bottom. So what is the complex conjugate of 2 minus the square root of 3i, or 2 minus 3i? 2 plus 3i. So we'll multiply the denominator by 2 plus 3i. But if we're multiplying the denominator by 2 plus 3i, we also have to multiply the numerator by 2 plus 3i. Okay. So on top, we're going to FOIL. First times first was 12. Outsides gets me a positive 18i. Insides, positive 2i. And last will be a 3i squared. We know 3i squared is negative 3. And then the great thing is in the denominator, because we've designed it this way and we've used the conjugates, we know our middle term's going away. So we'll have the first term times the first term is 4. Outsides gets me positive 6i. Insides negative 6i. They're gone. And last times last gets me a negative 9i squared, which becomes plus 9. I squared is a negative 1. So we simplify finally and say that this is, well, 12 minus 3, 18i plus 2i, and 4 plus 9. We no longer have a radical in the denominator. That's been simplified. Okay. All right, I'll let you do the next one. Make sure you know how to do these correctly, and we'll compare. We get 3 minus 14i over 41. Okay. Coming back to you. Everybody remembers this stuff? All right. So you do have a quiz tomorrow. It is not over this. Okay. Fairly long assignment. They're quick problems like these, though. They're not as long and absorbed as what we have been doing. So this assignment that I'm giving you is not due until Thursday, or I mean Monday. Tomorrow's your quiz over 2-1 through 2-3. 2-4 material you'll have time to work on tomorrow after your quiz, and then over the weekend having it due on Monday. Okay, so we have one more slide, I believe, and then we're ready to go. Yep. So complex solutions. So we talked about how now we can solve things like x squared plus 4 equals 0. So here's x squared plus 16 equals 0, something very, very similar. So how do we solve this guy? X squared plus 16 equals 0. Subtract the 16. Take it to the other side. Let's isolate that x squared. So if we take the 16 to the other side, we have x squared equals a negative 16. Opposite of squaring is square root, so we square root both sides. So now we get a plain old x. We have to remember that when we introduce the square root, we can't forget one of our answers, right? So what do we have to put in front? Plus or minus. Now, what is the square root of 16? 4. And what's the square root of negative 1? Because this is really the square root of negative 1 times 16. So 4 and I. And we have our solutions. They always travel in pairs. If positive 4i is one of our solutions, negative 4i has to be another. 0 plus 4i, 0 minus 4i. Okay? All right, next one. We're going to use the completing the square method to review what we talked about in section 2.1. We want to solve this by completing the square because we first look at it and we say we don't know of any factors of 24 that can add to become a positive 6, right? 12 and 2, 6 and 4, 8 and 3. Not working, is it? Okay. So by completing the square, tell me what the first step was. Subtract 24. We have x squared plus 6x equals a negative 24. Now, what do we have to do if we were trying to put that in vertex form? We take, yep. So what's half of 6? 3 squared is, but if we add 9 to the left-hand side, we have to add 9 to the right-hand side, right? And we didn't have a factor in a out in front that we had to worry about distributing through. So now we've made a perfect square trinomial. What is this perfect square trinomial? And what is negative 24 plus 9? Negative 15. Okay, now it looks kind of like what we had up here. The x is being squared, right? So the opposite of squaring is, so we square root. When we square a square root, we get whatever was under the radical. And that negative 1 under the radical is actually, what do we call that? I. So we can't forget about what? Our negative root, so plus or minus, right? And now we bring the 3 over to get the x all by itself. And so we will have negative 3 plus or minus I square roots of 15. 15 doesn't have a perfect square. We're done. And they always travel in pairs. So if negative 3 plus I square roots of 15 is one solution, negative 3 minus I square roots of 15 is another. Okay? Feeling good about this? Remember this stuff? Hopefully. Thumbs up, thumbs side, thumbs down. Okay, good. Looking confident. All right, so here is our assignment. Like I mentioned, it is not due until Monday. You'll have 2 days to work on it, and I have a review sheet for you. I'll get that to you too.